Direct analytical tone. A standard web application relies entirely on a primary database to store and retrieve information. Every time a user requests a profile, a feed, or an inventory count, the application sends queries to that central storage tier. Under heavy load, massive read requests cause the database disk to struggle, creating a latency bottleneck. To prevent failure, we position an in-memory cache directly in front of the database. Intercepting and resolving requests using RAM drops response times to sub-millisecond speeds. Functionally, this intermediate layer operates on strict instructions. It must support two basic operations: putting a new key value pair into memory and retrieving an existing value out based on its unique key. The physical constraint of this design is hardware capacity. RAM is highly performant but expensive and finite. A single cache server can never hold an enterprise application's entire dataset. Once the data outgrows a single machine's memory, the system must split that data across multiple distinct servers. To succeed at scale, this architecture must hit three distinct targets. It must maintain high read and write performance, scale horizontally for infinite data growth, and remain available despite hardware failures. Engineers cannot solve the scale problem by simply provisioning more RAM. The architecture must instead implement deterministic routing logic and automated cluster coordination across dozens of independent machines. Before scaling out to a wide network, we have to isolate the internal memory management of a single cache node. This diagram shows a hash map, the foundational data structure required for high performance. It allows the system to read and write items with an O of 1 time complexity, meaning the operation takes the same amount of time regardless of how much data is stored. Because RAM is limited, this hash map will eventually fill up. When the node hits capacity, the system needs an eviction policy to determine which piece of data to delete to make room for new requests. The most efficient strategy for this is the least recently used, or LRU, algorithm. It operates on a simple premise. If users haven't requested a piece of data recently, they are unlikely to request it again soon. A hash map cannot track chronological order. We solve this by introducing a doubly linked list. New data is inserted at the head. Requested older items are moved back to the head. When memory fills, the tail block is deleted. A hash map paired with a doubly linked list optimizes memory on a local scale, but it cannot bypass the physical limits of a single motherboard. To store more data, the cache must become a network. We move from a single node to a dedicated cache cluster. By utilizing multiple independent machines, we isolate system resources and vastly increase total memory capacity. The application server must deduce which server holds the data. The intuitive solution is naive routing logic. Compute the key's numerical hash, divide by the number of servers, and use the remainder to calculate the destination, routing to node 2. This modulo operation only works if the cluster is static. If a cache node fails, the denominator drops from 3 to 2. The altered divisor causes requests to route to the wrong servers, creating a tidal wave of database queries. Horizontal scalability is impossible if adding or losing a single node triggers a domino effect of cache invalidation that takes down the primary database. To prevent this systemic collapse, we replace naive modulo routing with an industry-standard algorithm known as consistent hashing. Instead of dividing keys, consistent hashing bends a massive address space into a continuous loop. Servers are assigned fixed locations on the ring. Incoming keys drop onto a coordinate and slide clockwise until they intersect with the first available server. To add memory, a new server is added to the cluster. This fourth server hashes onto a specific point on the ring, assuming responsibility for only a small subset of keys previously owned by its immediate clockwise neighbor. The location of all other servers remains static. The millions of keys stored across the remainder of the hash ring are completely unaffected. This localized redistribution allows engineers to add or remove servers at will. By isolating the changes to a single arc, the domino effect is neutralized. Consistent hashing solves horizontal scalability. But a critical vulnerability remains. If a server physically fails, the data stored exclusively on that shard is lost. When a shard fails, a specific partition of the hash ring goes blank. Every request routed to missing data becomes an unavoidable cache miss, forcing an expensive database read. To guarantee high availability, we implement leader-follower replication, duplicating data across physical hardware. Write requests are restricted exclusively to the leader node, while read requests are distributed across both leader and followers, increasing traffic capacity. This introduces a coordination problem. In a system managing millions of operations per second, how do client applications instantly know when a leader node dies? Manual intervention is not viable. If engineers use text files to push configuration updates, the delay is measured in minutes. The system will drop thousands of requests before the application realizes the network topology has changed. A configuration management service, like Apache Zookeeper, maintains a continuous heartbeat with every node. When it detects a dead leader, it executes an automated failover, instantly promoting a follower and pushing the updated routing table to clients. Achieving high availability means stripping state management out of the cache nodes. Relying on an external consensus tool maintains routing integrity entirely without human oversight. Broadening the scope, measured performance shows the distributed cache operating at enterprise scale. Local node performance is maintained by pairing the hash map with a doubly linked list, guaranteeing O of 1 time complexity for every individual read and write. The cluster scales safely because consistent hashing isolates hardware changes, eliminating the threat of mass cache invalidation. And the system guarantees uptime through leader-follower replication, monitored and automatically managed by Zookeeper's consensus protocols. But every feat of engineering requires a compromise. To maintain read and write speeds across the network, the data replication between leaders and followers is processed asynchronously. If a leader node receives new data but fails before syncing that record to its follower, that specific data point is lost. A read query sent to the follower will return a stale result, creating what is known as eventual consistency. System design is the art of balancing constraints. In distributed cache architecture, tight data consistency is sacrificed to push performance and availability to their absolute physical limits.